So although you can't actually then propagate pre and post conditions, for example, out of code you haven't analyzed, you can actually record what assumptions the caller is making. Okay, this is a little bit of a different situation. Now, let's say, okay, we've looked at the code. It's making sense. Have you got a test plan for this algorithm? One of the things that the analyzer can do is it can look at all the paths through the program. The cyclomatic complexity, that kind of thing, can tell you how many paths you actually have, which implies how many tests you actually need to some extent cover all the paths. But now you have to say, well, what actual values do I have to feed into the algorithm to exercise all those paths? Some of them may be fairly subtle. So one of the things that a tool like this can do is it can look at the algorithm and say, okay, well, it turns out you've got some numbers going in here, and they're not all different. Some of them all take you down the same path. So what this is saying here is the difference between high and low is relevant to the way the algorithm operates. If high is less than low, high minus low is negative, then some funny things are going to happen. You're going to do a different part of the algorithm. If it's greater than or equal to low, it doesn't really matter how much. That part of the algorithm is really going to operate exactly the same way. So you don't need to try all 2 billion of these different values to be sure that you've really exhaustively tested your algorithm. You might try, this one and that one and maybe one in the middle, but these shouldn't be really pushing different parts of your algorithm. Similarly here, this is a histogramming application, and there's it's being clipped. So if it goes above a certain value, then it's just treated like infinity. If it goes below, it's treated like negative infinity. So the value in a given element, so this is the array of things that you're trying to histogram. If it's greater than high, then you get into a certain part of the algorithm. If it's less than or equal to high, it's a different part. And that's the dividing line. So again, you need to have values in both sides of that, but you don't need to have 1,000 different values here and 1,000 different values. You can basically cut down your test suite to a fairly small range. This is the kind of thing you would want to know in your test plan for this algorithm. How are we going to be sure that we cover all the paths? For a lot of safety critical systems, achieving full coverage is a royal pain, and it can be a huge time sink. So if the tool can kind of get you started, okay, well, maybe we don't need to do all 2 to the third combinations here, but we do know that if we do all 2 to the third, we will hit all the different paths. Okay, so we've kind of looked at the function or the algorithm as a whole by using the tool's ability to propagate information out of a nested set of calls to summarize the properties. Now we're going to start looking at every line of code. This is where it really gets fun, right? And is there anything that we can do at that level, the line-by-line kind of analysis? Well, in some sense, this is what I think people have come to expect of static error detection tools, like Coverity has one for C, Clockwork has one for Java. There are a few of these other tools. And those are basically what they're trying to tell you is where can you fail? Where can a runtime check fail, or where can an assertion fail, and so on. So again, you'd expect that a static analysis tool can highlight the lines in your program where something might go haywire. It doesn't actually know what you're trying to do, but it knows what you're not trying to do. And you're not trying to exceed the bounds of various inputs. You're not trying to index out of arrays. You're not trying to go through null pointers and so on. So this gives you the line-by-line kind of thing. Okay, at this particular line, we've got some concerns about the overflow. These being out of range. This has to remain less than 80. This has to remain less than 24. In case you can't guess, this is one of those 24 by 80 cursor, old-style VT100 algorithms. And if these numbers get beyond that, the thing is going to just not operate the way you'd expect. So this is, again, it can look at every line and say, is there any danger that you will get any kind of failure here? If not, let's go to the next line. Let's not spend a whole lot of time on that one. But when you get to ones where there are some dangers, you've got to convince yourself that the programmer has done enough to make certain that won't happen. Okay, and then we've now finished our code review of all the sequential properties. Oh, 5, thank you. So that was the easy part, right? Now we got to worry about multi-threading. And is there anything that the tool can help us here? Well, actually, in some ways, this is one of the only ways that you can really find all the race conditions, because you can't find race conditions by just trying. You can bump into them, but you're not going to find them systematically by just trying it. So a static analysis tool is one of the best ways to help you in determining whether you have any race conditions. Here's an example of the kind of analysis it can do. One is it can find all of your entry points, your multiple threaded entry points, and it can distinguish between what you might consider reentrant entry points, like a task type would presumably have multiple instances. So that same amount of code is going to be running with potentially multiple threads at the same time. Or a singleton task object, which is just going to have one thread in it and never more than one, and so on. So knowing that, you can then begin to look at what are the objects being used by these threads, by these tasks, and is there appropriate amount of synchronization between the shared use. And in this case, it's complaining because we're using this delay time variable, and it turns out there are 2 threads that are using it. This one is speeding up things. It keeps just shrinking the delay time. Delay time gets delay time times 9/10. The delay time keeps going down. This is a game. It's Tetris, actually. And it gets faster and faster and faster. So you got one thread that's playing the game, another thread that is making it run faster, 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 faster. And they don't have any synchronization going on with this global. So that's the concern that's going on here. Now this is a simple value. Maybe it doesn't matter, but it's warning you. This is danger zone. And again, the program will have to decide, okay, well, it's safe because I've got this great proof that shows I'm not in trouble here. Okay, so wrapping up, code review is good for you, but so is flossing your teeth and eating all your vegetables, and we don't always do that. So is there any way to get us to do that code review? And our belief is that a static analysis tool can really automate the parts that you don't want to do. It can also give you much better information than you can get by staring at a listing. And the kinds of things it can do, all the inputs, outputs, the new objects being created, what are the expectations about those inputs and outputs from the algorithm? The preconditions, postconditions, these external calls, and what data you're doing that. Can it help you identify help with the test planning? Can it tell you what cases actually will throw the algorithm into different parts of throw the code in different parts of the algorithm? And what about runtime failures, sort of line by line kinds of things as well, concurrency issues and so on? And our feeling is that a static analysis tool is the way to do code review. You got to having that as your assistant makes the whole process a lot more reasonable, because right off the bat you can start comparing things like, oh, here are the requirements. What do we think the code is doing in terms of its inputs, its outputs, pre and post conditions? Is there a test plan for this code? How complex is it? And how many different test vectors are we going to need? And we got different values we're going to be running through it? And finally, it can help you understand just the overall structure, both sequentially and concurrently. Feels and becomes more productive, so you'll actually do it. Anyway.
Oh, good stuff.
Any questions? Thank you.